Thank you. Hello, everyone. I'm Claudia Colmo, and thank you for having me this afternoon. It's really exciting to share this knowledge. And my research is called Remediating Architecture, and my work fundamentally focuses on constructing a methodology using a bio-hybrid architecture system that symbiotically combine design components with mycelium to actuate in situ remediation of soil. We all know the most common use of mycelium as a composite. However, mycelium, other than be potentially a great material alternative, has so many more talents that in the right ways can be used to our advantages. And my research, in fact, follows the concept of microremediation and aims to create a framework which is environmentally suitable to keep the mycelium alive, allowing to utilize the organism both as a living part of the materiality, but also in perspective to use its incredible ability to restore fragile habitats. Take, for example, the city of Copenhagen, where I'm based. You can see that the contamination of soil is clearly concentrated around the urban areas. So I've been looking on the various remediation technologies, and the state of the art presents a vast repertoire. However, the remediation process is normally made by coupling various technologies, which mostly uses chemicals and excavation, and so causing a brutalization of the landscape. So microremediation is part of the bioremediation techniques, and this concept has been explored by Paul Stamets through his burlap bunker technology. And this technology consists in inoculated substrate that are placed in burlap bunkers, which are laid on the contaminated site. This represents the first attempt to scale up the use of mycelium for decontamination. But the potential here is that each species of mycelium has the particular enzyme that is able to degrade specific toxins. Therefore, combining different species, it is possible to create a synergistic effect for the contamination of various pollutants at once. To be able to apply this concept into these hazardous landscapes, it is fundamental to map the area with the types of toxins through soil sample analysis. And based on those contaminants, it is possible to select the combination of mycelium species. And here is the example of a site located in the heart of Copenhagen. My project aims, in fact, to functionally integrate this living organism in a way to develop customized mycological landscape for habitat restoration. And this methodology of the work is to use representations as speculative design proposition of a biohybrid system in which the mushroom guides the remediation process, and it's in symbiosis with the structure, and it dictates the lifespan of the structure. So the overall idea of the system is to use soil as the bulk material and incorporate living mycelium using digital design and fabrication through additive manufacturing. And the plausibility and the feasibility of the system are tested through material composition, fabrication, and biocompatibility. The material development starts from the material extraction, which happens in the site. And as you can see here is visible the high contamination level of hydrocarbons on the site. And in this particular case, the best mycelium species to decontaminate this toxin is documented to be the Pleurotus striatus, so the oyster mushroom. I collected the soil I refined it and processed it with the addition of bioadditives, which give this type of muddy appearance that you can see on the right photo. So the addition of bioadditives in this case is fundamental, not only to have an extrudable paste, but also is the way to set biocompatibility with the structure and the mycelium. Therefore, in this case, as a reinforcement component, I chose small hay fibers. And after a series of experiments, I selected the lubricants and the binding components, which are fundamental to have a paste, but also a compact material. And this was based on the quality, the selection was based on the quality of the mycelium film, which suggests a successful biocompatibility. So this material grade investigation produced successful soil composites and that are biocompatible and extrudable. And I made two recipes. Here is shown recipe A, which is composed by these 7 main ingredients, and recipe B, which incorporates embedded mycelium spawns in the material to test the feasibility for the fabrication to be the inoculation method. So the 3D printed setup is composed by a UR5, a liter syringe capacity where the material is placed and pushed by air compression, and a customized extruder with a nozzle of 7 millimeters. Then to set the quality of the print and to set the repeatability of the process, I've tested parameters for layer by layer deposition as layer heights and speed deposition, parameters to create strings within the structure, and the length of the strings. This is a way to create porosity in certain areas of the structure that allows air and light exchange, which are vital for the mycelium. So these various 3D printed tests allow to build the setup for the growth investigations, which are used to assess environmental parameters for promoting colonization of the mycelium, while promoting its role as structural binder and microremediation agent. So this was explored through the fabrication, the synthesis of two prototypes. The first is the double skin section prototype here, and the second one is a one skin section prototype. The type of geometry is made by a customized differential growth algorithm, and this geometry is found to be optimal since it increases connectivity between the scaffold and the mycelium, and the curvature assures stability while 3D printing. And from the basic geometry, the path was manipulated to create the strings. So the two prototypes have the same geometry, however, they differ in the inoculation method. So they both use the same strain of mycelium, which is the Chlorotus striatus. But in the one skin section, the inoculation is made post-printing, while the double skin section prototype is made by the fabrication process. And in both cases, no sterilization was used. So the setup here is a glass tank where a layer of contaminated soil is placed and two sections are placed on top. The prototypes were grown in a lab condition where there was control over light and humidity. And after the fabrication, the double skin prototype is filled with lignocellulose substrates and placed in the tank, testing if the mycelium would propagate from the internal skin, so from the walls, to the substrate, to the round substrate. And yeah, so the print was monitored over a period of about 30 days. And since the beginning, the growth was very slow. After 15 days, there were some signs of life. However, after the 25th day, the colonization appeared to be not consistent and very scattered. In fact, it looked like the mycelium after a period of growth regressed. So unfortunately, the idea of inoculation to 3D printing in this case was not feasible. We're passing to the one skin section prototype that was fabricated with a recipe A and not spawn embedded. The inoculation is made internally with non-sterilization and with a combination of hay and straw substrate and 10% of mycelium. After inoculation, the print was placed in the tank, and the growth was monitored over a time span of about 40 days. And already after the 5th day, there were signs of growth. And reaching the 15th day, the mycelium had quickly spread onto the section. And biocompatibility was established by the appearance of this primordial phase of fruiting bodies with agglomeration on the top and on the wall of the print. So after a bit more than a month, the mycelium transformed into this type of long stem mushrooms, which are both on top of the print and on the surface. But this physiology of the mushroom indicates a limited access to oxygen. So after a little tweaking of the environment, while the first generation started to decay, a second generation of mushroom appeared, looking more healthy. And it was able to reach the fully mushroom appearance with large cups. So here there are a few close-up photos showing the primordial phase of the mushroom evolution with this, and the stems were about 1 centimeter long. And was very interesting to see how the mushroom turned towards the source of light. And the mycelium covered the whole print and became an integrated part of the structure, creating this white hydrophobic coat that protected the print from water infiltration and therefore allowing better durability. So the first generation came out, as I said, with this long stem for a limited access of oxygen. And but the second one looked more healthy, and the evolution appeared faster than the first generation. And eventually it developed into these nice large cups mushrooms. With surprise, there was even the appearance of a third generation of fruiting bodies. And yeah, overall, the experiment was found to be incredibly successful. Biocompatibility was established by the appearance of 3 generations of fruiting bodies, and the mycelium formed that form on the surface had a really clear, nice network. And even there was no sterilization used. There were no signs of any other agents of contamination. So looking back to the overall microrestoration concept, the development of this methodology wants to give a new architectural expression to this micro remediation technology, and aims to set much more thoughtful relationship between the structure and the organism. And this symbiosis, in fact, has the potential to initiate an ecological succession. And in fact, the mycelium, due to the extreme environmental condition, is the only organism that is able to survive. And over time, though, the contamination opens up windows for various communities to settle and giving life, hopefully, to new ecosystems. So to conclude, my research presents a living demonstration of a biological integrated system that is functional performative, but also creates new opportunity to integrate different type of occupants while being ecologically positive. Thank you.
Hello, everyone. I'm Anna Goidea, and today I'll talk to you about our project for the Mycelium. But before that, I just want to say I think how exciting it is to see this community growing so much, and not just biodesign in general, but we're at the point where we have a full session on 3D printing with fungi. So I think that's really exciting. So really nice that you're.
There's one more session actually about 3D printing.
Okay, that's super exciting.
Yeah.
Yeah, I think that's really nice. So yeah, super nice initiative, Dylan, for organizing this. And yeah, thank you for inviting me. And I'm really looking forward to the discussion. So Protomycokeon is the demonstrator of the research project Pulp Faction that I've done together with David and Jean and with mycology support from Dimitrios Flodas. And maybe some of you are familiar with the project. I've also presented it a few times, including at Fabricate last year. But unfortunately, since then, I did not have the time to do more physical experimentation and testing. So it's the same project that I'll be presenting, but I'll try to show it some new things in a different perspective. So yeah, the project is sitting on 3 legs, let's say. The applied microbiology, which I've done in cooperation with the biology department at the ecology. It's a different institute actually from architecture at our university, and then digital fabrication at our 3D printing lab at the architecture building that we set up. And then, of course, it's all done under the umbrella of like research by design and architecture. But before I go more into it, I want to clarify some terminology. So we work with research by design, which is type of investigation which uses design as a tool of inquiry and knowledge production. So it's mainly using using the tools of design and prototyping mainly like with a strong material focus um, to test and iterate. And I think for this, it's really very compatible with biodesign and biofabrication. And transcalar design, we'll be releasing some more information on this. We have a paper on the way specifically talking about this, but transcalar design as a means of specifically in biodesign to target several scales, and also as it with the design strategy create interconnection and orchestrate the relation between different scales. And transdisciplinarity, which is of course a term that's being used a lot, but it mainly talks about a research strategy that combines different disciplines and in a way that transcends the structure of each discipline, right? The research output can be characterized when it's more than the sum of parts of each. And biofabrication, I think we all know, and yeah, the speakers, we all like work with this, but it's when the making of products that are using living cells as part of the fabrication strategy. And substrate and pulp, which I'm using a lot in this project as well, which is the mix of components onto which the microorganisms do the biotransformation. And then pulp is a substrate that has been inoculated with the living agent. So more practically, these are the actual steps to do in the project. Like we start by cultivating the strain, blending it, inoculating the substrate, then 3D printing with the living pulp. There's a period of growth in the shape, in the final shape, and then desiccation. So these are the steps that we've done so far. So it's not it's a describing methodology. So of course, a lot of the work is happening at the print lab, which involves all the digital fabrication, but a lot of the material research as well. And a good substrate has been very important in developing the research. So it's a mix of if it looks a bit like food, that's because it's almost edible, at least at part of it. It's mainly fibers, cellulose and wood, and then a thickening agent. And for the fibers, we've tested different types, including recycling. We had some really interesting results for a while with recycled cardboard from gypsum boards. There's a company that does these, but we've got some really good results and then not so good, then no growth at all. And probably that's because it's a bit hard to trace what is part of the, and maybe there is even some fungicide somewhere in the process, either in the use of the plasterboards or somewhere in the treatment. So we tried different types of fibers, but we ended up with ones that we could have have full knowledge of the source. So, and wood, and then later in the process, we added clay as a component for stabilizing the fabrication. And you can see here the progress when it comes to like printing and fabrication. On the left is some of the very early tests when we were just trying to figure out how to make the mix and print. And then in the middle, you can see some of the first successful prints with the living pulp, so inoculated with the fungus. And then to the right, when we had the protocol in place, and this is one of the components used in Paramycokeon. Oh, so this is one component after it's been printed, grown, and then dried. And this is how it looks, and then several of them put together. So even more of the work has been done at the biology lab, which we've been super fortunate to have a really, really fun and really exciting collaboration. Luckily, it's just across the park from us. So there's a small park between the biology and the architecture department. So it's been really easy to kind of move back and forth and iterate. And also, yeah, it's been a really nice journey of getting to grow and find out the methodologies, and of course learn the microbiology protocols that I haven't worked with microbiology before this project when it began in I think 2017, and then of course learning the protocols and navigating and bridging and modifying them to work for architectural purposes and scales. And these are the strains that we've been testing and done a lot of testing on. On the left, you can see Termitomyces, which is the original inspiration for the project, which is a fungal comb that is done by the mound building termites. And we've done the test and managed to take it quite far, but not far enough to have successful results on 3D printed structures. So then we've done the three others on the right that you can see. It's a Bisamarilius, a Leucopaxillus, and a Gleophyllum. And these are very different strains because they have very different decomposition strategies. And so we wanted to, with of course a limited amount of tests, try to span as much fungal behavior to see what works best for our case. So that's a white rot on the top, and then a litter decomposer, and a brown rot on the bottom. And it was the Gleophyllum that worked the best for the test and for the material properties that we achieved. And here you can see it on growing a petri dish to the left, and then on the substrate. So also done different types of growth on different mediums, on liquid medium and on solid medium, and it really depends what kind of fungal strain you're working with. Some really like growing on water, and some don't. So we ended up with growing on agar plates in the end. And yes, and we've been also sterilizing the substrate for the growth. And again, this really depends what kind of strain you're working with. There are some that are very resilient and can grow on many types of environments, and they even outcompete molds, right? Pleurotus, I think, is one of them. But the and then there's some that are almost impossible to keep sterile unless you're all the time in a lab in a sterilized environment. So a good compromise between speed of growth, resilience, but most importantly, the resulting material properties that we were after required that for our strain, we sterilize the substrate. So we've done this both through autoclaving, or this is in a dryer. And so after the step of inoculating, printing, there's a growth stage, and here you can see at the end of the growth stage, taking them out of the incubator. So you're incubating them at 25 degrees, right, which is almost like room temperature. They've been growing in these individual boxes. So these are the ones you see here. 2 are ready to be taken out. So we've been taking them. You can see the condensation on the box from the metabolism. So they're ready to be taken down and dried. And now I'll show you a video. So as we know that this is a time-lapse recording of the growth of a component. As we probably all experience, like working with living agents, right? It's a lot of the things are out of our control, and as much as you think you're doing the things right, sometimes it doesn't. And in this case, been taken over by a really annoying but really beautiful contamination. So yeah, as much as it makes for a nice video, it's not so useful for the production. But yeah, I think this was very much part of it, like learning what are the mistakes we've been doing, and how can we change the protocol and the methodology, and how can we improve, especially when taking things out of sterile environment and into an architectural one, which is non-sterile. So yes, but for in the end, for protomycokeon, like none of the bricks are contaminated. So we've redone the ones that got contaminated, and it's all with the strain that we selected. And then the design has been generatively driven, mainly a reaction diffusion simulation. I'm not going to talk about this today, as I've talked about it other times. So yeah, here you can see again a view of the column. And yeah, just to also just to say that protomycokeon has been exhibited at as an exhibition the end of last year in Malmö at Spark Gallery, where it was also together with time lapses, microscopy time lapses, and videos of fungal growth that I've taken. And also for the collaboration, it was really fun to have together with Michael Prime, who does these beautiful soundscapes of generated from electrical impulses from fungal growth. So that was a really fun thing to do. I mean, of course, a bit sad to have it in the middle of the pandemic. So, but it was, considering the situation, it was a lot of people came, and it was a really fun event. And right now, the column is being exhibited at Venice at Time Space Existence Biennale, together with our other project on bioreceptivity and integrating the functional different functions in architecture through 3D printing. So if you're in Venice until November this year, have a look. It's in Palazzo Mora. So yes. And yeah, just to wrap it up, like last month, we've gone at 3D Pioneers Challenge. We got an award for sustainability and material, and an Autodesk special mention. So I think it's quite exciting to see that even in fields outside of biodesign. I think people are really starting to appreciate the new alternatives, right, that come from biodesign and working with biology. So I think we're living in a really exciting period where I think more and more we'll see more and more of this. So yeah, thank you for listening.
Hi, my name is Natalie Lima. I'll be presenting my research of the bioscaffolds. Just a bit of background information about me. I'm from RMIT University. I'm a PhD candidate for Tectonic Formation Lab run by Roland Snooks. This research presented today is a collaboration between myself, Roland Snooks, and John McCormack from SensiLab. If you'd like to see more of our research, you can have a look at our Instagrams. For my one is biolab_studio. And here I really work a lot of work with mycelium, computational design, and robotic fabrication. The lab that I work for, Tectonic Formation Lab, directed by Roland Snooks, and SensiLab, which is directed by John McCormack at Monash University. So this research really focuses on the tension between biological agency and design aesthetic. And this research explores methodologies that extend design agency to the non-human. So by enabling this interspecies design, each project explores a negotiation of the architect's design aesthetic and biological growth through form. Within nature, nothing is still. There is a constant evolution of a time-based growth process and form. In order to embed these characteristics within architecture, I invite nature to become a co-creator within the design process. For this research, I've been working with mycelium. Mycelium is the fibrous root of a mushroom. Its chemical characteristics include its ability to act as a natural binder and adapts to any geometry provided. Fungi digest its surroundings in order to obtain energy and nutrients. It therefore grows by releasing enzymes from its tips, resulting in intricate tapestries of growth. When referring to mycelium's agency, this research is concerned with mycelium's fibrous root system and its structural capabilities. So rather than relating to nature for its form, similar to the biomimic process, this research is concerned with converting scientific observational knowledge into a language for architects to design with. This research therefore explores both a design that responds to mycelium's properties of growth and a design that responds to the organism's structural properties. When working with the living, we must consider the various types of agency and constraints that the material embodies. Through observational biological knowledge, this research focuses on mycelium's structural and growth agency in its capacity to generate form. Bioscaffolds explores a feedback that is more sequential within the design process. When design is generated, mycelium is infused and grown within the set framework. So as you can see here, the feedback system begins with observing biological agency. This research is reflected upon and catered for through design. Mycelium is then applied to these forms and observed and critiqued in order to inform the next design iteration. Bioscaffolds explores the robotic reading and infusion of liquefied mycelium into a series of biodegradable scaffolds. This research explores the orchestration of fungi growth by fabricating biological enclosures for the organism to inhabit. In response to the mycelium's micro patterns of growth when searching for nutrients, these heterogeneous skins orchestrate the growth and decay of mycelia through computational form and robotic intervention. By fusing robotic fabrication with living materials, I've been investigating the innovative technologies occurring within the biomedical industry, which include tissue engineering, printing artificial organs, and bioscaffolds. Specifically, I've been investigating the process of the medical bioscaffold. And through this investigation, I've been interested in how these methodologies of biodegradability and biocompatibility may occur outside the human body and be applied to the architectural discipline. So similar to the medical bioscaffolds, Mycelium is able to biodegrade through a range of fibrous forms in order to seek nutritious substrates. Through this research, I've discovered that mycelium is attracted to the fibrous properties contained within a wood-based PLA filament. It therefore has the ability to degrade any given mold provided, and as a result, I've been 3D printing a range of complex geometries with this fibrous filament and infusing them with the liquefied culture of mycelium. The prototype was then left to incubate as mycelium successfully began to grow and degrade the designated areas throughout the scaffold. With the intention of designing for decay, a series of computational skins were generated that encourage mycelial growth and scaffold degradation. Designing for non-human applications, these biological habitats manipulate the natural phenomena of life through a computational and robotic intervention. Through a process of color detection, I've developed an approach where data is extracted from mycelium through robotically controlled scanning and sampling. Through developed feedback systems, the robot was then enabled to verify which areas of the mycelium were living or dying. This occurred by robotically probing the mycelium with an Arduino moisture sensor, and in reaction to the value received, it would then rotate to inject additional mycelial culture. During the course of mycelium's development, the battle and the symbiotic tension between my machine and organism became apparent, transforming these biodegradable scaffolds into enclosures for mycelium to thrive and eventually adopt its overall geometry. By documenting the organism's reaction to each geometry, I've discovered that its ideal form for successful degradation is something quite fibrous, such as intricate lattice systems, providing pathways for the organism to latch onto and seep through, as presented here in this image. And so with this knowledge, I generated a series of lattice systems that would encourage the growth of mycelium and scaffold degradation. Here, I actually utilized a series of biodegradable bioscaffold softwares, such as N-typology, which actually generates scaffolds for medical use. In order to orchestrate the process of growth and decay through form, a series of skins were designed that would both discourage biological growth in the smooth areas and encourage growth within the lattice systems. Advancing this design concept, these two design languages of encouraging and hindering growth through form were fused together through 4 different algorithmic strategies. Through a sequential feedback system, each form was fabricated and injected with mycelium in order to examine the organism's response to the generated form. Critiquing these results, the forms evolved in complexity and detail over time. Developed by Roland Snooks, Algorithm 1, Painterly Forms, draws on the logic of swarm intelligence and multi-agent processes. These computational forms were then 3D printed out of the fibrous wooden filament and infused with mycelium. According to the experiment's results, the organism mostly reacted to the lattice-like areas for degradation, as seen in this image over here. With this knowledge in mind, the second iteration of this design was developed in order to further enhance these features of feather-like strands, resulting in a gradient of elongated fibrous strands with non-indexical forms. These new iterations were 3D printed and tested with the organism. Evident in these images here, the mycelium creates web-like structures branching from each digitally fabricated antenna. These results were examined in order to inform the next design iteration, which further exaggerated these design features. These forms have been 3D printed and will soon be inoculated with mycelium. So by researching through design, each form has evolved according to the results observed from mycelium's inoculation. Due to this recursive feedback system, a catalogue of forms is produced, advancing complexity and detail over time. Within the second algorithm implemented, differential growth, form is growing through an algorithmic process, which is actually not dissimilar to the patterns of growth seen in nature. These forms were 3D printed and inoculated with mycelium. And so from examining these results, currently I'm computationally mutating these skins in order to further enhance these highly articulated areas for mycelial growth. Based on the logic of a distribution of meshes, the third algorithm generated array cells across the designed surface. These forms have been 3D printed and are currently being inoculated with mycelium. With an understanding of how mycelium could react to these forms, I have been testing a number of geometries with these intricate skins that could further enhance the organism's behavior. The final algorithm of this series, differential growth, is based on generative curves adapting to a surface. Currently, these forms are being robotically fabricated and infused with mycelium. So the aim of this research outcome isn't to produce one finalized form, but rather a catalogue of geometries showcasing contrasting biological patterns of growth. Whilst initially the algorithms were developed according to the architect's aesthetic, the observation of biological growth disrupts the design process through a sequential feedback system between architectural and biological agencies. As you can see in this form finding catalogue here. So if you'd like to follow more of our research, please follow us on biolabs_studio on Instagram. We'll be posting further work on this developed research. Thank you very much, and I'll see you next time.